Hi everyone, welcome back to the Coding and Analysis YouTube channel. And in today's video, I'm going to run the XGBoost. It's cross-validation applied model. So this function trains a specific XGBoost model using a 5-fold cross-validation and find the best number of boosting rounds. Then it's going to fit a final model, all the data for that position, and returns predictions versus the actual ESPN25 predicted PPR points. So we're going to name our function train and predict underscore CV. Like the previous video, we just named it train and predict, but now we're adding the CV for cross validation. I'm importing the importing XGBoost again as XGB just because we want to use XGB as an alias. So we have what we're going to do here, like we did in the previous video, for the most part, is we filter players by their position. So right here, so this is the fantasy positions could equal the running back, wide receiver, tight end combined, and the quarterback. And then we're using the historical stats and health and age data and risk tier and projected roles as this feature, as these feature columns, as the X, and then we're using the Y as the target variable for the ESPN 2025 PPR, and then we reset the index for clean processing right here, and then we're going to train the final model, and then we're going to once we train the model, we predict. So we train it. It's going to predict fantasy points for all the players, and then combine all the results. So let's get into that. Talk about that. So when we reset it right here, so this is our new data frame. This is the original data frame. I'm making a copy of it. So this is the new data frame, position underscore data, filtered on all the all the positions. So that's why you see the running backs first, because it's been filtered on the positions, running backs. And the second one you see wide receiver, tight end, and third you see the quarterbacks. If we didn't filter on that, it would all be jumbled. Like up at the top, you have some quarterbacks, some wide receivers, some running backs all together, but we're separating them all out by position. So we're ensuring right here, we're ensuring the line indices across all the structures, and then we convert data to the D matrix for XGBoost. So we're saying D matrix equals the XGBoost, but we're using XGB as the alias. So we're getting this D matrix out of the XGBoost, and then we're putting in our feature columns with the X, and then the label, the target variable is the Y, and then these are going to be the parameters that we're going to use. And so at the objective for the regular, so I guess it's the regression problem, squared error. So it specifies this is a regression problem predicting continuous values. And now we're going to have the max depth of 3. Each decision tree is shallow, only 3 levels deep. Helps reduce overfitting by limiting model complexity. Then we're putting the learning rate, standard learning rate, as the 0.1 controls how much each new tree corrects errors from the previous one. Lower values mean more conservative learning. And then we're having the lambda is 1, and then the alpha is 0.1. So lambda is, I guess lambda is the L2 regularization. So it penalizes large weights in the model, similar to ridge regression. And so that means it's going to try to, anything that's above 50%, I guess, like the guess it's because try not to get anything over more than 50. So it's trying to keep it down 50, 55, I guess, for the highest features. And then alpha, so that's the L1 regularization, so that encourages sparsity, pruning unnecessary features, similar to the lasso regression. So just remember lambda as ridge regression and alpha is the lasso regression if you want to go do more research on that. And then the seed is 42, ensures reproducibility results, and then the eval metric is MAE. That just means we're using the mean absolute error to evaluate model performance during training. And then you can see here we're getting our 5-fold cross-validation with early stopping to avoid overfitting. So all these params are going to be in here. And then, so XGB, so that would be the XGBoost, the alias, .cv. So we're doing splitting the data into 5 folds, and it's going to train the model on 4 folds, validates on the remaining fold, and it's going to repeat this process 5 times, rotating the validation fold each time. So when we see the params, so we're bringing the params from all this that we put in here, and then we're saying D train is going to equal to D matrix. And then the boosting rounds is going to be the trees, max trees that we're going to use. And then the early stopping rounds, we're going to put the 10, stop if no improvement for 10 rounds. Then the metrics we're going to put as MAE and the seed 42, and then the verbose evaluation suppresses the print output during the training. So then once we get all that, we're going to say we want to determine the best iteration, lowest validation MAE. So what we do here is we get finds the boosting round with the lowest validation MAE, and then retrains the final model on all data with the best number of trees. So once it figures out which trees it's going to use on the best number of rounds, and then it's going to print out the CV results, and then it's going to train the final model using all the data in the best number of rounds right here. So we're saying model is going to equal the XGBoost.train, and then it's using the params up here and the D matrix up here that we put in, and then it's going to use the number of the best boosting rounds that the model determined, the best iteration. So it's, instead of just putting 150, it's going to put the best right here, the lowest validation MAE results. And then we're generating the predictions right here. So we're just saying, hey, look at our hey data frame position underscore data. We're making a new column called predicted fantasy points, and then we want that to equal the model and the predict on the D matrix, and then we're going to return the results right here. And then once we get the parameters, so these are the features right here. This is the position, just like in the previous one. So these are the positions, these are the column features, and then we concatenate the results. Shows running backs first, wide receivers tight end second, quarterbacks third. And then we're going into our override dictionary, doing a for loop, and then once we do the for loop, we're telling it our data frame which which players we want to put a 0, and then the notes for why we want to put a 0. And we're saving the results right here. CV xg underscore CV2. Since the first one without the 2, it was with the CBS model, but the CV2 is going to be with the ESPN model. And this is their predictions, what's going to show up on the CSV file. And then, so the best MAE for the running backs was 38 points. For the running backs, so 38 points, mean absolute error at 61 rounds. So I guess at 61 trees. Let's see, let me go back and look at that. So yeah, so best number of rounds. So it's really the stopped at 61 rounds, and then 55 rounds, that was the best. MAE 37 points, and then 50 quarterbacks at only 18 rounds. Since really there's only, I guess there's 39 quarterbacks, so it really doesn't have to go too far with only using 18 rounds. So 61 running backs to recap, and went up to 61 trees. The boosting round, the max number of trees, so 61 for the running back. Our receivers, tight ends, it's 55, and then quarterback is only 18. So really, I guess think of it as the more the trees. So if we had like 500 running backs, 500 wide receivers, tight ends, it would probably go up to like 100 or maybe 150 trees. But since we're only doing 88 running backs, it's only getting up to 61 trees, and then I think we're doing 180 these combined. It's getting to 55 trees. We're at 39 quarterbacks, so it's only going into 18 rounds. So let's look at in the next video, I'll evaluate the R-squared and the MAE score for the cross-validation, finding the, so we did, to recap, we did the cross-validation model with the XGBoost. So XGBoost plus cross-validation, and then we found the best iteration or lowest validation MAE, and we trained the final model using all the data and the best number of rounds for the position. So that's what we did, and let's look at the results in the next video.